Okay, now you have a question to discuss and answer. So you have this dipole configuration, in fact, a positive charge and a negative charge, and you bring a third charge from infinity to the middle of them. So what is the work that you should do to bring it from infinity to the middle of these two charges? Okay, not even 30 students had sent their answers. You have 2 minutes more. If you send your answer, you can discuss with your friends. Okay, so let's start with A. Why do you think it is positive? Okay, what was your answer? D. Okay, so +1 for D. So A, do you want to explain why do you think it is positive? Any volunteers? Okay, why B? Well, the competition was mainly between A and C. Why C? Somebody else? Okay, so your answer is basically, if there is no force, then there is no work done. And you are saying that at the midpoint, the force will be 0, and hence there won't be any work done. Anybody who agrees with him, disagrees with him? How many of you agree with him? Okay, you are all wrong. The answer is correct. Your reasoning is wrong. You see, at the midpoint, there is no force, but as you are moving it from infinity to the midpoint, you are passing all these regions where there will be some force.
Okay, I wasn't completely sure. Can I?
Okay.
So, what I think what we know is the electric potential of infinity is 0. And,
no, we don't know that. We define that.
Yeah, that's why we know. Yeah, anyway. So, the electric potential in the middle of those two black holes is also 0.
Why?
Because they both contribute in different ways. I mostly visualize them as like hills and drops, like in a 2D sense. So like minus charge is like and positive charge is like a hill, and between them there is this area which is 0. And, that's right in the middle. And our equations support that. What we know that we're just taking it from a point which is 0 to a point which is 0. So so it doesn't change. It's supposed to be 0.
Okay. Anybody who agrees, disagrees with him? I mean, you might agree with his conclusion that it is 0, but disagree with his explanation.
Where is the minus changing the potential energy? So potential energy is the independent from the path. So it's the difference between the last potential energy and first potential energy. It might be 0.
It might be, or it will be, or it is 0. Somebody else? So how come it is 0? So you're passing all these places where there is some force acting on it.
Because it's a conservative force, and when you study that conservative forces, basically they don't depend on the path taken, they depend on the initial and the final. So the initial is 0, the final is 0, hence the work done by the fall is 0, because it's a conservative force.
True, but that's the definition, kind of, that's all your friends are saying. But my answer is, how come the work done at different steps add up to 0?
It's not 0 because it's an equilibrium point and it's not cut off.
Stable?
It's not a stable equilibrium point. If it's moved right or left just a little bit, it would be release its potential.
True.
And
But
it's not 0.
so is it positive, negative, or you cannot determine it? Which one was your answer?
It would be positive at one side and negative for the other side.
Well, you see, you are just carrying this charged object from infinity to this point. the total work that you do is either positive, negative, zero, or you cannot know, or, I mean, it cannot, or since it's conservative, it cannot depend on the path. You know your initial point, you know your final point, so it's either positive, negative, or you might not know it.
I don't know.
You don't know, or you are E. E or D?
Yes, no.
Okay, you are E.
I don't know if it's positive or
Okay, so it cannot be determined. Not enough information is given.
well, actually, I didn't see the question really, but
Hocam normalde futbolun ortasında, tam ortasında bir dikey olarak eş potansiyel düzeyidir, değil mi? Bu eş potansiyel düzeyde hareket ettiği zaman herhangi bir iş yapılmaz. Yani eşitliğe göre. Yani potansiyel enerjideki değişim deneme güç çarpı şey olarak tanımlanıyor ya. Potansiyel enerji şey. Elektriksel potansiyel farkı. Bu da elektriksel potansiyel farkı olmadığı için herhangi bir potansiyel enerji değişimi olmuyor, iş olmuyor. Yani savunma
So, let me repeat my second question, not the question here. But my question is this one. You are basically saying, most of you are saying, the potential difference is zero, so the work done is zero. The potential difference is, the work done is nothing but the charge that you are moving around times the potential difference. That's the work that you do. But the question is this one. So here I have a plus Q charge, here I have a minus Q charge. And let's assume that I'm just moving it from here to this point. This is the midpoint. Here the force acting on my Q prime charge will be, as one of your friends said, that it will be zero. First of all, will it be zero? Let's imagine it's a positive charge. Now plus charge will be pushing it away, minus charge will be pulling it, so the force will be in this direction. So there is a force over here. Net force is non-zero. Here there will be some net force, and the direction of the net force will be somewhere like this. Here it will be in more or less in this direction. Here it will be, I don't know, in this direction. And somehow, although if I just consider, let's say, this very small step, there is some work done at that very small step. The total work done is zero. Yes?
ne kadar uzaklıktan o dipolun tek bir sıfır charge'da tek bir point charge olarak görünmesinden
No. Well, you see, this as one of you had, I mean, at least for one path, we can explicitly see that the work is zero. Well, basically, you can just take it along this path. You see, along this line, the electric field will be always in this direction. This is E. But your displacements are in this direction. So the electric field and the displacements are zero. So along this special path, at least, at every step you do zero work. So that's why even if you come from infinity, you are not doing any work. Now for this other path that we considered over here, well, let's say I kind of draw it. This is not correct. The electric field over here will be something like this, because the negative charge is closer, so it will have a more dominant effect. The electric field will be somehow pointing in this direction. So you see, as you are moving in this direction, at this point the electric field is pointing in this direction. This is the direction of your motion, this is the direction of the electric field. So E dot dl is positive. So there is a positive contribution to work from this segment. Now if you consider this segment over here, this is your displacement, this is the electric field, they are kind of in opposite directions. So the work done is negative. So here there is a positive work done, here there is some negative work done, and the sum, it just turns out that it cancels. Why it cancels completely? Well, we know from this path. It should be independent of the path. In this path, the sum is zero, so the sum in this path should also be zero. So although there are forces everywhere acting on my object, the work done is still zero. because the point here, as most of you have pointed out, the potential at this point is the same as the potential at infinity, so the potential difference is 0. So although, as one of your friends had also made the analogy with hills and wells, you might be going uphill during some path or downhill during the other path, but the net change in your height between this point and infinity will be 0. So again, the work done will be 0. Now let's discuss one concept that you would like to use, which we haven't discussed yet, the equipotential surfaces. Now, do you have any questions before we continue to equipotential surfaces? Well, you see, now if you consider the work that we have done, let's just imagine we are bringing some positive charge from infinity. To calculate the work that we have to do, we have to first calculate how much force we have to exert to move it with a constant acceleration, constant velocity, constant speed. And the force that we have to exert will be the sum. We should cancel the electrostatic force. So it should be equal to, at least in magnitude, the sum of the forces due to the positive charge and due to the negative charge. Now, if positive charge was not there, we will be doing some amount of work to bring the object up to this point. And if negative charge was not there, but the positive charge was there, so we will be doing some other work. Now, if both charges are there, the net work that we have to do will be just the sum of these two works. Now, let's first imagine we don't have this positive charge, we only have the negative charge. And we are bringing one positive charge. Okay, so there is the negative charge, we have the positive charge, so there is an attractive force in that direction. We have to exert a force in the opposite direction. This is the direction that we are exerting, the force that we are exerting. So this is the displacement. The charge is slowly, with 0 acceleration, moving to its final point. This is the force that I am exerting. They are in opposite directions. So basically, I will be doing negative work against the force exerted by this minus Q charge. Now let's look at the plus Q charge. The plus Q charge will be pushing my plus 1 charge. So the force that this plus Q charge will be exerting will be in this direction. So I should exert a force on my charge in this direction. So this is the direction of the force that I am exerting. I am moving towards the positive charge until I reach the midpoint, that point over there. So this is the force that I am exerting. This is the direction of my displacement. I am doing positive work against the force of this positive charge. And I used to do a negative work against the force due to this negative charge. So I have a positive work, negative work. If I sum them up, I do 0 work. The work that I do with respect to both of them will be equal in magnitude but opposite in sign. It's not an equilibrium point. There is a force acting on it. It's neither stable nor unstable. It's not an equilibrium point. Well, the force, if I put a charge over here, it will feel a force in this direction, and you know the Newton's dynamics, do whatever you want. Okay, now let's look at this equipotential surfaces. Now let's go back to this example, where we had this delta V is equal to minus E delta L cosine theta. Now, before we looked at the points for which this delta V was a maximum, well, depending on the direction, delta V can be positive, negative, because the cosine theta will change its sign. And before we first looked at the special case when delta V was maximum as a number, And we said that that corresponds to cosine theta is equal to -1, and we had all the consequences. Now we can also look at points for which delta V is 0. If cosine theta is 0 or theta is equal to pi over 2, plus or minus pi over 2. Now let's consider what this theta is. Suppose here there is a region, this is the direction of the electric field. Now theta is the angle between the electric field and this dl vector, right, that I consider. This is the electric field and I can take this dl vector, so this will be my theta. Or I can take this theta dl vector and this will be my theta. Do you agree? Now theta is equal to pi over 2. If I take this dl vector, that will be theta is equal to pi over 2. Or if I take this dl vector, theta is again pi over 2. So all the points on this arc, or in fact this disk for all the dl in this direction, this theta is pi over 2, so delta V is 0. Do you agree? So I have I have this point, this is the electric field at that point, and I have all these points, nearby points, which have exactly the same potential. Well, if you consider all those points that are very close by, they just form a disk, a surface. Do you agree? Those on the back? Do you agree? Okay, so I have this point. The electric field is somewhere in this direction. And there is this small disk around this point, which all these points are equipotential, at the same potential. That's what we mean by equipotential. They have this equal potentials. Now I can look at this point over here. There will be some electric field also in this point. It will be almost in the same direction, but maybe slightly shifted. But then I can determine some other disk over there. And then I can determine another disk. And that will give me a large surface. All of these points will be at the same potential. That is what we call the equipotential surface. Well, one property is already obvious from the way we defined it. At every point on this equipotential surface, at every point there is an electric field, and any vector on this surface makes 90 degrees with this electric field. So the surface is perpendicular to the direction of the electric field at every point. This is one property of the equipotential surface. Now let's look at some examples which will hopefully make it more clear. Point charge. We know that the potential at a given point created by this point charge is 1 over 4 pi epsilon 0 q over r. So this is the potential. So potential only depends on the distance from your point charge. So if you consider the points whose distance from this point charge is the same, well, those points form an equipotential surface because they will all have the same potential. R is equal to constant defines equipotential surfaces. For every constant, you have an equipotential surface, a different equipotential surface. So this is one equipotential surface. Well, is it perpendicular at every point to the electric field line? Yes. Well, I mean, we know that for a point charge, the electric field line is radially outward, and the radially outward vector is always perpendicular to the surface of the sphere whose center is your origin. So this property that the electric field lines are perpendicular to the surface is kind of obvious from here. Now this also allows you to determine the equipotential surfaces, at least to be able to sketch them. Let's look at the dipole. Now we know the electric field lines of the dipole. We had already discussed it. Let's suppose we have a plus Q charge, a minus Q charge over here. Now the electric field lines, well, let me have more space. Plus Q, minus Q. The electric field lines will have this formula. So this is the sketch of the electric field lines. Now we have to draw some surface that is perpendicular to all these lines. That will give us the equipotential surfaces. Let us try to determine the equipotential surface that passes through this point. Well, let's see, it will be here perpendicular like this, and so it has more or less this shape. It looks like a circle. Now if we want to draw the equipotential surface passing through the middle, you see at the middle along this line, so the electric field lines are pointing in this direction, electric field. So this line itself is an equipotential surface because everywhere it's perpendicular to the electric field. And in fact, if you draw the electric field lines, this is how they will look at different points. And in fact, if you want to determine the mathematical shape of these equipotential surfaces, mathematical expression for these, you see for a given point, let's say this point, let's call this distance from the minus Q charge R minus, and this distance from the plus charge at R plus. Equipotential surfaces will be, you see the potential at this point, P, is 1 over 4 pi epsilon 0, Q over R plus, plus minus Q over R minus, Q over 4 pi epsilon 0, 1 over R plus, minus 1 over R minus. So equipotential surfaces will be mainly determined by this expression, 1 over R plus minus 1 over R minus is equal to some constant. Different constants give you different equipotential surfaces. In fact, it turns out that if you try to solve this equation, you will see that this basically describes spheres. Equipotential surfaces for the dipoles are also spheres. They are not centered at the charges, their center moves away from the charges. But never, you see, you start from the plus Q charge, there's a sphere over here, and this larger sphere has the radius move towards the left, and the radius also gets larger and larger. Eventually the center goes to infinity, the radius goes to infinity, this is the one you get. And then the center goes to infinity over here with radius equal to infinity, and the center gets closer and closer and closer until here you get, for example, a sphere with center here, radius close, small. Now the equipotential surfaces, usually when you are plotting them, you just fix some potential differences. For example, you say that you draw an equipotential surface for every change of 1 volt. So it might be that this is the corresponds to 1 volt, 2 volts, 3 volts, 4, 5, 6. Can it be possible? Can this be 1 volt, 2 volt, 3 volt, 5 volt, and 6 volts? Yes? So you are saying that you can choose these charges Q and their separations such that this will be 1 volt, 2 volt, 3 volt. You see, let's just take this line. As I go from the plus Q charge to the minus Q charge, does the potential drop or increase? You see, let's look at the change in the potential. Delta V is equal to minus E dot dl. If I move along this line, I'm moving in the direction of the electric field. So dl and E, they are pointing in the same direction. So if you have two vectors that are pointing in the same direction, if you take their scalar product, that's a positive number. So delta V should be negative. So as I'm going from the plus Q charge, from a point close to the plus Q charge to a point closer to the minus Q charge, delta V is negative, that is the potential should be dropping. So the potential cannot be plus 1, plus 2, plus 3. It cannot increase, it should decrease. I can start from, let's say, 3, 2, 1. This will be the zero potential line, 1, 2, and 3. Or minus 1, minus 2, and minus 3. That's possible. 3, 2, 1, 0, minus 1, minus 2, and minus 3. But you cannot go 1, 2, 3, 4. The potential should be dropping as you go from plus Q to minus Q. Because you are moving in the direction of the electric field. Now, why is the electric field perpendicular to the equipotential surfaces? Again, because of this relation. You see, if you just pick up any 2 points on the equipotential surface that are sufficiently close to each other, so that in that region, electric field is constant, let's say, then delta V is 0 because we are only on the surface at which every point has the same potential. So delta V is 0. So E dot dl should be 0. The electric field need not be 0. The only requirement is that the electric field and the difference between the position vectors of those 2 points should be perpendicular to each other. This is on my surface. dl is an arbitrary vector on my surface. So E should be perpendicular to my surface on an equipotential surface. Again, this is just a way of visualizing the electric field lines. And by just looking at this graph also, you can, this equipotential source is a way of visualizing the potential, but also of electric field lines. Look at here. So you see, at this region, the equipotential surfaces are, assuming that the difference between the potential between two neighboring equipotential surfaces is the constant, you see their density is lower in this region, but larger in this region, the density of the equipotential surfaces. So again, just like the density of the electric field lines gives you an information about the intensity of the electric field, the density of equipotential surfaces also gives you an idea about the intensity of the electric field. Now, any questions on equipotential surfaces? Sure, I mean, of course, you can choose your numbers. You can choose your charge or the distance between them to make sure to fix the potential of this sphere to a given value. By increasing the charge, you make sure that the potential here is larger. The potential at this middle plane should be 0. You cannot change that. 0 times some number is again 0. But you can change the difference between two successive equipotential surfaces by changing the charge.
If you put a charge on an equipotential surface, how it would behave, that charge?
So let's say you put a charge at rest. Okay, that's the simplest thing. On an equipotential surface. Well, it will feel a force due to the electric field. What will be the direction of the electric field? To the lower, it will be perpendicular to the surface. So that will be the direction of the electric field. That will be, if it's a positive charge, it will be the direction of the force. If it's negative charge, it will be in the opposite direction. So the force will be in the opposite direction to this equipotential surface. It will accelerate in that direction. Again, these surfaces, these equipotential surfaces, are just the constructs, some mathematical constructs that will help you to visualize the electric field. Any questions? So if I tell you that the surface of a conductor is an equipotential surface, do you agree?
Yeah.
Why? This is the question. The surface of a conductor is an equipotential surface. Why?
Because the charge in the conductor creates so they're moving apart.
Okay.
That creates some potentials that if the surface is, if the conductor is uniform.
No, I talk about, let's say, such a conductor. And I still claim that the surface is an equipotential surface, the surface of the conductor.
Is it supposed to be neutral? Or can it be very...
No, not necessarily neutral. It can be charged. It can have cavities. You can put some charges in the cavities. I don't care, the surface, or you can put some other charges over here, outside. So let's put a positive charge. So there will be some negative charges accumulating here, some positive charges accumulating on the other side. Still, the surface of the conductor will be an equipotential surface.
Because it will be zero.
What will be zero?
So,
The potential need not be zero. I'm not saying that the surface is a zero potential. I'm saying that the surface is an equipotential. The potential can be non-zero or zero. I don't know. Depends. Depends on your system. Still, it will be an equipotential surface.
I think the electric field in the conductor is zero.
Yeah, that's basically the idea. Let's take this point over here, P0, and this point over here, P1. The difference in the potential will be just the integral of E dot dl from P0 to P1 through any path that you can imagine. I can imagine such a path. Because electric field everywhere along this path is zero. It's inside a conductor. If electric field is zero, the potential difference is zero. In fact, any point inside the conductor is also at the same point, so it's in a sense equipotential volume, let's say. Well, we don't have that concept, but nevertheless we have the equipotential surface. The surface of the conductor will be equipotential surface. The inside surface will be also at the same potential as the outer surface. They will have the same potential because of the same reasoning. But this also gives me, as a corollary, tells me that the electric field on the surface of a metal, of a conductor, let's say, is always perpendicular to the surface. since the surface is an equipotential surface, and we know that the electric field is always perpendicular to the equipotential surface, the electric field should be always perpendicular to the surface of the conductor. Now that also just a reminder in electrostatics. If we are not doing electrostatics, this need not be true. But in electrostatics, the electric field has to be perpendicular to the surface. Well, that kind of makes sense because if the electric field is not perpendicular, it means there is a horizontal component of the electric field. But if there is a horizontal component of the electric field, then it will exert a horizontal force to the electrons. Let's say a metal. Well, the metal just prevents the electrons from moving out of the metal, but it doesn't prevent the electrons to move horizontally to the surface. So if there is an electric field horizontal to the surface, the electrons will move horizontally to the surface, but that's not electrostatics. So once we reach electrostatics, the electric field will be perpendicular to the surface. Questions? Which solid angle?
Electric fields independent of the shape, harmonic colored surface.
No. Other questions?
You said that you just said the electrons, once they reach electrostatics, the force, the electric field must be perpendicular. And I agree. But why should we reach electrostatics and push later?
So what do you think the electrons will keep doing?
Maybe they keep moving.
They keep moving. Let's see, what kind of an electric field will you be trying to generate? You see, let's say we have this circular shape and you want to keep the electrons moving around this circle. That means you need to be creating an electric field, a circular electric field.
So they eventually stop at some point.
Unless you are able to create circular electric fields, they have to stop. And we will see later on that you cannot create circular electric fields so easily. Not in electrostatics, at least. You cannot the electric field lines, they have to start from some positive charge and they have to end in a negative charge, or they go to infinity. You cannot form such closed electric fields in electrostatics. We will see cases where in electrodynamics, we will see cases where you do actually create such electric fields, circular. They form closed loops. They don't start from positive any charge. They don't end at any charge. They just form these loops. But that is dynamics, when you have moving charges.
But if we have a charge inside the surface,
So?
then we have an electric field.
Now you see, we have this cavity and inside we have a charge. Is this what you mean?
Yes.
You don't have an electric field in the conductor. You see, if you put some charge over there, let's say a positive charge, what will happen is the electric field lines, they will just start and move to, and they will be perpendicular to the surface. They will terminate on the surface. They will not go into the conductor, because the charges in the conductor will accumulate on the inner surface until the electric field in the conductor is zero. Okay, see you after the coffee break.